So we know that data inside the computer system is represented in bits and binary. So I'm just going to talk about a little bit more about that representation of data. We know everything is stored in binary code. It doesn't matter if it's Word, Excel, documents, images, music, video, whatever they are. And we know that those patterns of ones and zeros are called a bit, which is short for binary digit. That's where the BI and the T comes from in bit. And we know that we tend to talk about bytes, which is 8 bits, and even bigger amounts of zeros and ones, kilobytes, megabytes, gigabytes, and terabytes. And that 8 bits is called a byte. So for example here, we'd actually have 6 bytes. There we go. How many amounts of 8 do we have here? Well, we've got 6, so that would be 6 bytes. So how do we actually represent numbers? Well, this is where we can lean on number theory, because binary patterns often are used, those sort of patterns of ones and zeros are often used to represent denary numbers, base 10 numbers. So let's just do a quick little bit of talk here about sort of number bases. Base 10, another name for that is denary. It's the number system that we use all the time, and obviously it has 10 symbols that we use. So we have the symbol 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Well, binary is base 2. So denary base 10, binary is base 2, and that means that instead of having all of those particular symbols, we can only use 2 symbols, 0 and 1. So you can see it naturally fits in with computing, because computing can store 0 and 1 values. Now in base 10, in denary, each column is worth 10 times more than the previous one. So if I write a number down like 12,563, we can write that down using what I'm sure is a familiar column notation to you. What that actually translates into is 1 10,000, 2 thousands, 5 100s, 6 tens and 3 ones. And then if we add those all up, we get that 12,563 figure. Now another way of looking at that is, if you like maths, if you look at the top row, what we're actually suggesting is that each column is worth 10 times as much as the column before. So it could actually be written down and look like this. Anything to the power 0 is 1, so that first column on the right is 1. 10 to the 1 just means 10, so that's 6 tens. 10 to the 2, well that means 10 times 10, which is 100, so that means 5 100s. 10 to the 3 is 1,000, 10 times 10 times 10. 10 to the 4 is 10 times 10 times 10 times 10. And so all of that is added up to give you that number of 12,563. Similarly then, let's have a look at a base 2 number. Well, in base 2, each column is worth twice as much as the previous column. So for example, say you had this binary number here, 10110. Well, we could write that down using the grid notation. So each column, starting from the one on the right, is worth twice as much as the column that it's next to. So you can see how the numbers go up, 1, 2, 4, 8, 16, and then we just carry on going. And when we place a 1 or a 0 in there, what we're indicating is that we either want that value or we don't. So that would actually translate into 116, no 8s, 14, 12, and no zeros, and you add those all up and you would get 22, just like that. Alternatively, if you like maths, just as we did before with the base 10 table, what you could do is you could replace that top line with things which are to the power of 2. So anything to the power of 0 is 1, so we've got a 1 in the far right column, and then we've got a 2, and then 2 times 2, which is 4, 2 times 2 times 2, which gives you the 8, 16, 32, etc. all the way along. So we would simply add all that up, and that means that 10110 in binary would be 22 in base 10. And notice how often we use that subscript notation here, 22 with 10 in tiny little letters as a subscript to indicate that's a base 10 number. So imagine you had this number 1678 in base 10 and you wanted to know what that actually was in binary. Well, if we had this grid here, so these are a grid where every column is worth twice as much as the one that it's next to. And what we could do is we could just find which one of these numbers are required to make up 1678. So we could start from the left and we could basically just put zeros and ones in to indicate whether it's needed to make up that 1678. So we could start over here and we could basically go, do we need 1024? Now, 1678 is obviously bigger than 1024. So yes, that would be a really good number to use. So if we place a 1 in there, what that means is we now need to make up the rest of that number using the remaining columns. So 1678 take away 1024 gives you 654, which we need to make up from the remaining columns. And what we're going to do is we're going to place a 0 or a 1 in here to indicate we need to include or exclude that column when it's all being added up. So we just progress along from left to right. So we've got to make up that 654 from the remaining columns. Can we use 512? Yes, we can. So we can place a 1 in there, which means from the remaining columns, we've got to make up 654 minus 512, which gives 142. So now we move on and we go, okay, well now we need to find 142 and 256 is bigger than 142, so we can't use that. So we just simply place a 0. Keep going. Still got 142 to get, so we move on to the next column, which is 128. And 142 is bigger than 128, so we can place a 1 in here, which would mean that we would need 14 more. So we need to get 14 more from these remaining columns. So we just keep going. Can we use a 64? No, so we place a 0. Still looking for that 14. Can we get a 32? No. Much bigger than a 14, that's no good. Still need to get that 14. Can we get a 16? No, 16 is bigger than 14, it's no good. Place a 0 in there. Ah, here we go. Suddenly we get to the remaining 4 columns. And yes, we could use an 8. And what that will do is we'll place a 1 in here, and that means that we have 6 to get. And we just keep going. Yes, we can use a 4. So we place a 1 in here. 6 take away the 4 gives you 2. And we're nearly there because we've got a column with a 2. So we can place a 1. And then we could just fill the remainder of the grid, however many columns there were, with a 0, because we've actually got it now. We can actually make up that 1678 by using 1024, 512, 128, an 8, a 4 and a 2. And so what we've actually done is we've found the binary pattern that corresponds to that base 10 number, just like that. And notice how I'm indicating the base by using the number in subscript here. So 1678 base 10 is 110100011110 in base 2. What about if you had to go the other way? Well, let's say that you were given that number 11010001110 in binary, and you wanted to work out what it was in base 10 in denary. Well, you draw the grid, put the numbers in the grid, just like this, and then add them up. So we've got 1 1024, 1 512, 1 128, 1 8 1 4 1 2, and that gives us the number. We just add them all up and we get that 1678. Now there is an alternative way of doing this, and of course the alternative way is to simply use a calculator, which is what most people do now, of course, do nowadays, of course. So how is that actually relevant to us? Well, for example, how do we represent colours? On the web here, by the way. We know we've got those built-in colour names, aqua, black, olive, purple, grey, green, whatever. But what we're actually doing here is we're representing colours as a binary pattern. And on the web, colours are done by using amounts of red, amounts of green, and amounts of blue. And what we're really doing is we're saying how much red, green, and blue there will actually be. Now, this is obviously quite commonly this is abbreviated to RGB, amounts of red, amounts of green, and amounts of blue. So what that would actually translates into is a binary pattern, a number between 0 and 255 of an amount of red and an amount of green and an amount of blue. Now, if we have no red, no green, and no blue, we get black. If we had all the red, all the green, and all the blue, and the maximum number there is going to be 1, 1, 1, 1, 1 all the way across, we get white. And other colours are formed by using different amounts of those numbers. So for example, here's a kind of blue colour, and you can see that's created by using this amount of red, this amount of green, and this amount of blue. Now these numbers are written down by writing them in the RGB order. So if we were to actually write that colour down, it would look like this. So that is the binary pattern that would represent the blue colour on the previous slide. Now it would be nice if there was a shorthand way of actually doing this, because obviously that's a bit of a hassle writing all those ones and zeros down. And this applies not just to colours but just to binary patterns in general. And there is a way of doing this, because what we can do is we can use hexadecimal. Now hexadecimal is another number base, it's base 16. And often hexadecimal is used in computing all the time because it is, as I've indicated, a shorthand for binary. We know that binary, which is base 2, uses 2 symbols. Denary, which is base 10, uses 10 symbols. And those are the particular symbols in each case. Well, hexadecimal is base 16. So that will require 16 symbols. So we can start off by using those symbols, but we've got a problem because we've sort of run out of symbols. So what we'll do is we'll steal some symbols from the alphabet. We'll use the letters A, B, C, D, E, and F for the numbers 10 through to 15. So here are some example hexadecimal numbers. They look like this. So sometimes they've got letters in and sometimes they don't. How is hexadecimal a shortcut? Well, there's lots of different ways of doing this, but probably the easiest way is have a look at this shortcut table. You can see how each hexadecimal digit represents a 4-digit binary pattern. So what's the quick and easy way of converting a binary number to a hexadecimal number? Well, let's imagine that we wanted to represent this binary pattern as a hexadecimal pattern. All you do is you would take the binary pattern, you divide it into blocks of 4 from the right. So here you can see it's exactly the same number. All I'm doing is just gathering them up into groups of 4. Now, if the number on the far left doesn't actually have 4 digits, then just add some extra zeros on the front. And all we do is we replace each 4-bit pattern with the hex digit that comes from that table. So we would simply go through and each one is replaced with the digit. So 0111 is a 7, 0000 is a 0, 0100 is a 4, just like that. And that's the actual hexadecimal number. So we know that this binary pattern corresponds to this hexadecimal number. And often we would write that down by using a 16 to indicate the base in subscript, or an H. On the web, and particularly in computing, sometimes we'll use that little hash symbol to indicate that it's a hexadecimal number. And again, most people use calculators. If you want to find the colour representation for a particular colour, in other words, what the hexadecimal colour is for it, you would typically use one of these tools that are available online, and it will give you the hexadecimal number that corresponds to that colour. And as I've indicated before, the nice advantage of representing colours as numbers is there's lots of mathematical theory that allows you to work out what are complementary colours, and there are tools available that will do that for you.